Hello students. So last time what we have seen is the depletion type MOSFET, and we were discussing about the symbols for depletion type MOSFET. So this is the symbol for depletion type MOSFET. So we have already seen in the class that there are four terminals. One is gate terminal, drain terminal, source terminal, and body terminal, substrate terminal. So if this is the arrow is from the arrow direction decides whether it's an N channel or it's a P channel. So the arrow is always from P to N. Okay, so P to N meaning it's an N channel because the N side is towards the channel sides, so we call it an N channel MOSFET. Okay, however, if the symbol is outside meaning P to N, meaning the channel is P and the body is N type, so we call it a P channel MOSFET. Okay, however, if you have a three terminal gate, drain and source, if the body terminal is also attached with the source terminal, then the symbol direction or the arrow direction is same. However, you have only three terminal over here. Okay, but the concept is same. The arrow direction is always from P to N, so it's an N channel MOSFET. Okay, so these are the symbol. Okay, for depletion type MOSFET. Now come to the enhancement type MOSFET. I already told you in the lecture that in enhancement type MOSFET you have a MOSFET something like this. Suppose you have an N channel MOSFET, so you have to start with a P substrate. So this is a P substrate, and P substrate you have to make the source and drain. So this is your N plus and this is your N plus, source and drain. So this is your source and let's say this is your drain. Okay, so here you don't have any channel over here. Here you don't have any channel. However, in case of a depletion type MOSFET, you already have a channel over here. Here you don't have a channel, you have only the oxide layer over here and you have the metal layer over here. So you have metal, so this is your metal, this is your oxide, and this is your semiconductor. So you have metal, oxide, semiconductor, but you don't have a channel. So if by applying the gate voltage, so this metal is known as a gate terminal. So by applying the gate voltage, you can create the channel over here, and that's why we call it a enhancement. So basically we have enhanced the channel over here. So in this case we have enhanced the channel, so we call it a enhancement mode or type MOSFET. Okay, so how we can construct the N channel enhancement type MOSFET? Let's see. So basic constructions, let's see the basic constructions as substrate of P type material. So here you need to take a P type material over here, as I just now told you, and you need to make two portion in this P type substrate, which is N. So this is also N, this is also N, and then you need to have an oxide layer over here. So this is your oxide layer. So these dash line with this dash line and this white color is your oxide layer, and then you have a metal contacts. So these are your metal contacts. So this is one metal contact which is over the oxide, and this is a metal contact which is directly on this N region on the drain, and this is the terminal on source. Okay, so if substrate of P type material is formed from a silicon base, so here you have a silicon base, and on the silicon base, as with the depletion type MOSFET, the substrate may be internally connected to the source terminal or a fourth lead. Okay, so it depending upon that you have a 3-terminal MOSFET or you have a 4-terminal MOSFET. If it is a 3-terminal MOSFET, then the substrate will be internally connected to the source, or if it is a 4-terminal MOSFET, then it will be different as a SS terminal. Okay, so two N-type doped regions are there. So one is this N-type doped region and one is this N-type doped region are there in the substrate by diffusing N-type impurities. And how this N-type region formed? So using diffusion. Okay, so you diffuse the impurity in this particular region and you make it source and drain. One of the region is called drain and the other region is called source. Okay, the source and drain terminals are connected to N-doped regions through metallic contacts too. So the source and drain terminal are connected to N-doped region. So this source and drain terminal are connected to this N-type region. So these are directly connected to N-type regions. Okay, and known as source and drain. This is a silicon dioxide layers, and typical thickness is 1000 angstrom. Okay, 100 nanometer. Isolates the gate metallic perform from the substrate. Okay, no problem. The primary difference between the depletion type and enhancement type MOSFET is the absence of channel between the two doped regions. So here you don't have any channel. Okay, if you wanted to flow the current from source to drain, let's say, you need to create a N channel over here. And how can you create an N channel over here? So you need to apply a positive gate voltage over this. I already told you in the class also that when you will apply a positive terminal, so this will behave a parallel plate capacitor. You have a metal plate over here like this. You have in between oxide layer, which is a dielectric, and you have again a metallic layer over here, because this is semiconductor, and semiconductor is a half conductor only. So this is your M2, and let's say this is your M1. So if you will apply positive voltage on the metal plate 1, the other plate of the metal will get negatively charged. Okay, so the electron will come over here. So here you will have something known as a N-type semiconductor instead of a P-type semiconductor. So you have created a channel. When you have created a channel, when you have applied a positive voltage to the gate terminal. Okay, so as soon as you apply a positive voltage to the gate terminal, there will be a channel. And now if you will apply a VDS like this, suppose if you will apply a VDS like this, then this electron from the source terminal will move towards this side, towards the drain side, and there will be a IDS. Okay, so what does it mean? For N-channel enhancement type MOSFET, a threshold voltage VG has to be positive to make it on. To make it on, VG has to be positive. Okay, so these things you should keep in your mind. What is the symbol of enhancement type MOSFET? So only difference is here you show this line, the vertical line, by the dashed line. Okay, here you don't have a solid line nahi hai yahan pe. You have only the dashed line meaning there is no channel. You have to enhance the channel, you have to create a channel in between. Right now there is no channel. Okay, so that's why there are dashed line over here. The only difference is this. Okay, so in case of a depletion type MOSFET, you have something like this. So like if you have a 4 terminal, so this is the symbol. Okay, so this is the depletion type because you have a solid line over here. However, in case of enhancement type, you have something like this. So this shows that the channel is not there. You need to create a channel over there. Okay, so this dash line shows there is no channel. So yes, like this. Okay, so these are the symbols. So this is for 4 terminal N channel MOSFET, this is for 3 terminal N channel MOSFET. The only difference is here the substrate, here the body is isolated from the source, here the substrate is get connected internally with the source. Okay, so it is the only difference between the symbols of depletion type and enhancement type MOSFETs. So the dash lines and all. The next topic is very important topic, is types of logic families. Okay, so how you make the NAND gate and how you make the NOR gate, or how you make the AND gate. What are the what is there inside the AND gate? Suppose you have an AND gate like this. Okay, so what is there inside the AND gate? Whether the transistors are there sorry, whether the CMOS, whether the MOSFET are there, whether the BJTs are there, whether the diodes are there. Okay, so depending upon what is there inside of this AND gate or NAND gate, we have different logic families. Okay, so the entire range of digital ICs are fabricated using either या तो उसके अंदर क्या होंगे bipolar devices, there will be bipolar devices, or there will be a MOS devices, or a combo of two, and that family is known as a BiMOS. So it is, some portion of the gate could be bipolar device, using the bipolar device. Some portion of the gate can be made using the MOS devices. Okay, so depending upon how the device is made, how the gate is, how the logic gate or how the IC is made, so we call it's a bipolar kind of a device logic family, or it's a MOS device logic family, or it's a combo of two BiMOS logic family. Okay, in bipolar also further divisions are there. In bipolar there could be a diode logic, there could be a resistor transistor logic, there could be a diode transistor logic, there could be a I2L logic. Okay, generally not used nowadays. So there could be a TTL logic family, there could be a ECL logic family. Like this, there can be many logic family in case of a bipolar families. Okay, in MOS, PMOS generally not used. I already told you the reason, because in PMOS, hole are the majority charge carrier, and hole have the smaller speed as compared to the electrons. So PMOS is normally not used. Either it's a NMOS family, meaning if an AND gate is made, it is made completely using NMOS. We call it a N-channel MOSFET logic family, NMOS logic families, or this AND gate could be made up of using CMOS family, using both NMOS and P-channel devices. Okay, so now the third type of logic families is BiMOS logic families, where both bipolar and MOS devices are used. So these families vary by speed, power consumptions, cost, voltage and current levels. Okay, in some of the devices you may have a greater speed, in some of the devices you may have a speed is higher but the power consumption is let's say less, okay, or let's say high, or the cost is high, let's say. So there are trade-off between speed and power consumption and between cost, like this. So in some devices you may have a very good speed but you have a also you have a very high power consumptions. Okay, so now let's consider the NAND gate, how the NAND gate is formed using the TTL logic family. Okay, so this is the basic structure of a TTL logic family. TTL is basically, in this you have transistor logic. Okay, you have a diode but still it is called TTL, transistor logic. Okay, so this circuit, this complete circuit is basically a circuit of a NAND gate. Okay, so how does it work? Let's see. So in this the main thing is, in this, let me show you here. In this is a emitter coupled transistor. So here you have two transistors, basically both have same base, both have same collector, but they have two different emitters, E1 and E2. The emitters are different, meaning you can make the transistor something like this. So suppose you have this transistor like this. Okay, let me show you the transistor something like this. So let's say this is emitter P, this is base N, and let's say this is collector P. Okay, so let's say this is a PNP transistor. So what you have done is, so let's say in P you have made two different regions like this. So this is also P, this is also P. So these two are emitters only. The collector, the base is same, the collector is same. You have two different emitters. Okay, so this is how also you can make a PNP transistor. So in this you have two emitter coupled basically transistors. Okay, now how does it work? The important thing is how does it work. So these two emitters are basically the input of the NAND gate, and this is your output of the NAND gate, and this is your VCC, and this is your ground. Okay, so now you can make it a symbol like this. So if you wanted to make a symbol, you can make a symbol like this. So this is your basically this is your NAND gate. Okay, so here you have a output, here you have two inputs like this. So now how does it work? This is very important. ये work कैसे करता है? Let's see this. So let's suppose this both the inputs are, let's say, high. Suppose both the inputs are high. If both the inputs are high, so let's say these are at 5 volt, and let's say this is VCC is also 5 volt. Okay, so what does how does it work? Okay, so let's understand that. So if you have a 5 volt over here, so that means you have a base over here which is at 5 volt, and you have this emitter also at 5 volt. So definitely this transistor, the current will flow like this. The current will flow like this. The current will not flow towards this side, because this transistor is what? So this transistor is P, N and N. So NPN transistor is there. So if this is at high, so N is at high, P is also at high, P is also at 5 volt, N is also at 5 volt. Definitely this will be in a reverse bias. अगर हमें पता है N भी अगर 5 वोल्ट के ऊपर हो और P भी 5 वोल्ट के ऊपर हो, this will be in a reverse bias. So the current will flow like this. Okay, so what does it mean? It means that the Q1 transistor, this Q2 transistor, this transistor name is Q2. This Q2 will be in a saturation, because there will be high base current flowing towards this side. So if Q2 will be in a saturation, हमें पता है in saturation VCE, this voltage is generally 0.2. This I have already discussed in the lecture कि अगर कोई transistor saturation में होता है, तो saturation में ये जो voltage होता है, this voltage is generally 0.2 volt. So that means this VCE will be around 0.2 volt. Okay, so now if this will be in a saturation, there will be a large IC. Large IC is flowing like this. If the large IC is flowing like this, then the Q4 will also be in a saturation. Why Q4 will be in a saturation? Because there is a large IC is flowing, and this IC is behaving, this IC is also IB for Q4. Okay, so Q4 transistor will also be in a saturation. Okay, so if Q4 will be in a saturation, so let me erase it and then let me show you very important thing. So if Q4 will be in a on mode and this is also on, so this transistor is on, this transistor is on, so now we need to consider that what will be this voltage. हमें ये दिखना पड़ेगा कि यहाँ का voltage कितना है. So what is this voltage? So this voltage is 0.2, And what about this? So this is your PN junction diode. So this is your PN junction diode. And we know that in PN junction diode, what is the voltage drop? If it is on, so this is 0.7. So that means this is at ground. So this is at 0. So definitely this has to be at 0.7 because हमें पता है कि base to emitter there has to be a maximum 0.7 volt. So if this is at 0.7, this is at 0.2, so this will be at 0.9. Okay, now if this is at 0.9, what do you think that Q3 will be on or off? So definitely the Q3 will be off. Why Q3 will be off? Because this 0.9 voltage need to drive two PN junction. One PN junction is this and one additional D1 diode is there. Okay, so this 0.9 voltage cannot run two different diodes. Okay, अगर दो diodes को run कराना है, so how much voltage you will be requiring? 1.4 volt, 0.7 for this diode and 0.7 for this diode. So at least you should have here 1.4 volt. Then only Q3 will be on, otherwise Q3 will not be on. If Q3 will not be on, so let's erase it and understand it again. So this is at 0.9, and since there is a 0.9 volt, this cannot drive Q3 as well as D1, so this will be off. If this will be off, what does it mean? This VCC is not connected with the Y. Y is connected with the ground because Q4 is on. If it is on, so Y is connected to the ground. So that means if the inputs are high, Y will be low, and this is the working of NAND gate. So this is the working of a NAND gate. Okay, similarly, so let's see what is the written over the PPTs. The two emitters are two inputs of the NAND gate, no problem. D2 and D3 are used limit negative input voltages. Okay, when both the inputs are high, the current, yes, this we have already seen that Q1 will be on, Q2 will be on, Q3 will be off, Q4 will be on. And this produces a logic low at the output. Yes, this we have already seen. When output Y is low, Q4 is in saturation. Yes, Q4 is in saturation. Q3 mainly conduct in the absence of D1. अगर यहाँ पर D1 नहीं होता तो Q3 conduct करता, but diode D1 prevents transistor Q3 from conducting even a small amount of current. So this diode is preventing. Okay, so when either of the low inputs or both inputs are in the logic low state. Now the another case, so we have already seen that if A, B and Y is your output, so we have already seen if AB is 1 1, output is 0. Now we have to consider these three cases. Okay, so if both the inputs are low or either one input is low, then we have to understand that how the output is high. Okay, so let's understand that. So let's erase it and let's understand now. So when either of the two inputs or both inputs are in the logic low, the base emitter region of Q1 conducts current. So if this is low, let's say if this is low and this is high, or this is high, this is low, any of the input or both the inputs are low. So if any of the input will be low, so this will conduct the current like this. Okay, so there will not be any current towards this side. Okay, what does it mean? It means Q2 will be off. Directly Q2 will be off. If Q2 will be off, Q4 has to be off because the collector of the Q2 is the base of the Q4. So definitely the Q2 and Q4 are off. Q2 in the cutoff state and Q2 in the cutoff state. So then Q4 is also in a cutoff state. Q3 is driven to conduction. So now the Q3, since Q3 is, so this VCC is connected over here. So definitely this Q3 will be in on conditions. So if the Q3 is in on conditions, so definitely, so this voltage will be over here because this is on. If this is on, then the VCC is directly over here, and Q4 is off. So definitely the output is not at 0 volt. It is at something around VCC. If let's say VCC is 5 volt, there will be some drop over here, and there will be some drop over here, and there will be some drop over D1 across D1. So what will be the output? Output produces 2.4 volt at least, and in logic family 2.4 volt is considered as a logic high. Okay, so this is how the TTL NAND gate works. Okay, and the final topic in logic family is CMOS based devices. Okay, so CMOS based devices is also very important. So right now we have seen the BJT based devices. Now we will see the CMOS based devices. So how does it work? So CMOS based devices meaning when you have both the P channel MOSFET and you have N channel MOSFETs. Both you have on a single piece of a semiconductor. So the problem is the P channel MOSFET can be made on a N substrate, we know that, and N channel MOSFET can be made on a P substrate. Okay, so how to make CMOS devices on a same substrate? So what people have done is, people have, let's say, taken the N type substrate, okay, and in N type substrate they have made this let's say this one, this tub. Okay, so they have created a tub. In N type substrate they have created a P tub. Okay, P tub, and in this N type substrate they have made a P channel MOSFET, and in P tub they have made a N channel MOSFET. So this is how they have made a P channel MOSFET here and an N channel MOSFET over here in a single device, and this device is known as a CMOS device. Okay, now let's consider how does it work. Okay, so let me show you how does it work. Okay, and before telling that how does it work, so let's understand some points. So I told you number one point, that in N channel MOSFET conduction is there when gate to source voltage is positive. Just now, 2-3 slides back, I was already telling you that when N channel MOSFET is there, you need to have gate to source voltage which is positive, then only it will conduct. Similarly, for P channel MOSFET, gate to source voltage has to be negative, then only it will conduct, otherwise it will not conduct. So either type of device is turned off, its gate, if its gate to source voltage is 0. Okay, so these 3 points you need to remember to understand the operation of CMOS device. Okay, so let's understand the CMOS device. So this is your CMOS device. So let's say we have a PMOS over here, let's say we have a NMOS over here, and let's say the drain of NMOS and the drain of PMOS we have connected like this, and let's say this is the source of PMOS, and let's say this is the source of NMOS. Okay, so now let's understand this. So let's say this input, let's say this is your input. Okay, so let's say both the gate of both the transistors, let's say we have tied together, and let's say we are giving the input of at this point, and let's say we are taking the output at the drain of both the transistors. Okay, so now let's say the input is 0. Okay, so what do you think, what will happen? Kya hoga? Which transistor will be in a working state? So let's say this is a 5 volt. Okay, and let's say this is a 0. Okay, so this is source of P, this is drain of P, this is drain of N, this is source of N. Okay, so now you need to understand which transistor will be on. So this is a gate of P and this is a gate of N. Okay, what is the VGS over here? If I ask you what is the VGS, so S is at 5 volt, G is at 0 volt, so VGS is negative. Okay, and what the rule we have written, the P channel MOSFET conducts when its gate to source voltage is negative. So definitely this PMOS will conduct. What about the NMOS? So the G is at 0, S is at 0, so VGS equal to 0. So definitely the NMOS will not conduct. Okay, if PMOS will conduct, what does it mean? If this is conducting, it will show 0 resistance. If it will show 0 resistance, so definitely this 5 volt will be at output. So when the input is 0, the output will be 1. Okay, so now consider this other case when the input is high. Let's say the input is also 5 volt now, and let's say this VDD is 5 volt. So now this S is at 5, this G is at 5 volt. What is the VGS? So VGS will be 0 volt over here. So what does it mean? The PMOS will not conduct, off. You can write over here off. Now here the gate is at 5 volt, source is at 0, so VGS will be what? VGS will be positive. Okay, and when in N channel MOSFET, if VGS is positive, it conducts. So that means it will conduct. If it will conduct, it does not produce any resistance. So what does it mean? This point will be at ground because this is a conducting path. If this is a conducting path, whatever the resistor, whatever the voltage over here, the same voltage will appear over here. So this voltage is at 0, so definitely this will be at 0. So if the input is 5 volt, the output will be 0. So the CMOS basically behaves as a NOT gate directly. Okay, So this is basically the working. When the input is low, this we have already seen, both gates are at zero potential. The input is at negative potential related to the source of the P channel, turning the P device on. For the N device, the input is at zero related to the source of the, thus turning it off. Okay, so under these conditions there is a low impedance path from VDD to output. So this is a low impedance path and to the output, and a very high impedance path from the ground. So this will be a very high impedance path. Okay, so let me erase it, and now you can see. So you can see this is on basically. So this is your output. This output will be at VDD, and this is a very high impedance path. Okay. And when input is high, this is a very low impedance path, and you have a very high impedance path over here. So the output will be at 0. So if input is 1, output will be 0. If input is 0, output will be 1. So now we have already seen that NAND gate using TTL earlier. Now let's consider a NAND gate which is based upon a CMOS device. Now how easy it is, let's see. So this is your NAND gate using CMOS. So here you have two PMOS devices and you have two NMOS devices. You have two input over here and you need to take the output over here. So it's very easy now. So if let's say A and B both are high, let's say both are high. If both are high, what will happen? So let me erase it, and now let me show you. So if this is 5 volt and this is also 5 volt, okay, so now you can see, so this is the P source. So since this is B is at 5 volt, so definitely this gate is at 5 volt, and this is at 5 volt, so definitely this is at 5 volt. So here source is also at VDD 5 volt. So definitely VGS will be, in both the cases, VGS will be 0. If VGS will be 0, PMOS will be off. Both the PMOS devices will be off. What about the N-type MOSFET? So here the gate is at 5 volt and source is at ground. So if the source is at ground and the gate is at 5 volt, VGS is positive. And in case if in N-channel MOSFET, if VGS is positive, it conducts. What does it mean? The output will be at ground, because both the devices are conducting. So definitely the output will be at ground. If any of the input is 0 volt, let's say if this is at 0 volt, if definitely this will be at 0 volt, so this will not on, this will be off, and this will be on. So this VDD will be here at the output. So if any input will be low, the output will be high. So if both the inputs are high, so let me erase it. Let me erase the complete slide. Just a second. Yes. Okay. So if both inputs A and B are high, A and B equal to 1, both P channel transistors turn off. So these are turned off, these are turned on, N channel get turned on. The output Y has a low impedance to the ground and produces low state. So you will get 0. Okay, if both the inputs are high. Now if any input is low, let's say B is this low, so this will be off. Okay, this will be off, and correspondingly this will be off, but this will be on, so the output will be at 1 volt or logic 1, you can say at logic 1. So how can you make the CMOS NOR gate? So in CMOS NOR gate you have a P in parallel there. In NAND gate you have P in series and in parallel. However, if you wanted to make a NOR gate, P in parallel and in series, P in series and N in parallel. Okay, so now again, if what is the NOR gate? AB is equal to F 001 011 000 010 100 and 11 is 0. So 00 is 1. So this is the truth table of a NOR gate. 0 पर ये हमको 1 देता है, and rest of the combination, whenever there is any input is 1, the output has to be 0. So this is NOR gate. So if both the inputs are 0, let's say A and B both are 0, so what will happen is both the P-type MOSFETs get turned on. If they get turned on, this VDD will be at output. So if this is 0, this is 0, output will be 1. If any of the input will be 1, if let's say this is 1, this P type MOSFET will get off and this N type MOSFET will get on. So if this get on, so this output will be connected to the ground. So the output will be 0. Okay, so it's written over here. So let me see what it is written. A and B both are 0. Yes, if both are 0, P type will be on because this VGS will be negative. If both the P type will be on, the output will be at 5 volt at high state. If any of the input will be 0, the corresponding N MOSFET will be on and the P MOSFET will be off. Since they are in a series, so definitely if any of the input, any of the P type MOSFET will be off, definitely the output is not connected with the VDD. But since these are in parallel, so if any N type MOSFET is on, the output is connected to the ground. So if any of the input is, let's say A equal to 0, the corresponding N type will get on, the output is connected to the ground, becomes 0. So low level output. So in this lecture we will keep till here only, and we have one more lecture regarding operational amplifier that we will see in the next lecture. Thank you.